program that was actually conducted. Then I will again walk you through the closed loop dynamic testing methodology that's been proposed and applied in this research, and will sum up with the conclusions. So as everybody already knows, I guess, in this room, that mainly there are three lateral force resisting systems that typically used more than any other systems. And mainly we are talking here about the diagonal bracings or different types of bracings in different configurations, shear planes or shear walls, and rigid joints, or what is called or named as moment resisting frames. So in this research, I am focusing mainly on bracings in general. So typically there are, again, three types of bracings. The most, let's say, old kind of bracing, which are conventional or typical bracings that are mainly composed of typical HSS sections or some steel, usually, components. And the other type, which is more recent type of bracing, which is the buckling restraint braces. And then the very recent types of bracing that started emerging into the research and industry is the self-centering bracing. So how bracings work, as I said, one of the most widely used systems, and you can see them in different buildings, is that when an earthquake or lateral load is actually applied to the braced frame, then one component or one element of the braces will be under tension and the other one will be under compression. And as we know, seismic or lateral loads can, most of the cases are reversed cyclic loading. So the initially brace that was under tension will be under compression, and the one under compression will be under tension. Now, this is the way it works, but when we look into a bit more details, how actually each type of this system behave. So if we consider a conventional brace, under tension it works, it takes the load, it yields, yeah, but still it takes the load without much of loss of strength and stiffness. However, in compression, after a few cycles, it will generate or have some plastic hinging, and then the strength and stiffness will degrade, and which will lead to some kind of failure. So it may cause some safety issues into the occupants of the building, not to mention also the economic losses. So these are just typical failure modes of conventional bracings, which involves both in-plane and out-of-plane buckling. And as I said, even if it doesn't lead to complete collapse of the building, you will eventually need to replace these elements, probably also replace the neighboring elements in terms of beams, columns, joints, which impose huge economic losses. Now, if you look into the buckling restraint braces, so yeah, they have been proposed to actually solve the problem of buckling as we see in conventional bracings, but again, it yields. It yields in both tension and compression, which means, again, the building will stand safely, most probably, but you will have, again, to do repair and maintenance costs. In extreme cases, again, you may have to demolish the building because it's not economic to repair it anymore. That's where self-centering bracings come into the picture, and as we'll see in their different configurations, they are actually behaving in a reliable way in both tension and compression, so they provide to great extent a sustainable and safe solution. So you don't need to actually do lots of repair in most of the cases, and then you achieve a more resilient structure. So if you move to the next part, which is about the experimental program. So before I go into the details of the system and the experimental program, the main component that actually this system works on is shape memory alloys, which have such kind of behavior as you see here. So if we look into the stress strain behavior of SMA, as you can see, after a certain yielding point, it goes to a super elastic range where it can take lots of deformation. The specific type that's been used in this research is the nitinol or nickel titanium SMA, which can have 6 to 8% of restored super elastic strain. So after removing the load, it will return to its original shape. We will see more in details how to model this and all the different aspects of this material, which is a potential candidate in bracing systems. So a little bit of details about the system itself. So the system employs, as I said, shape umber alloy that was machined, and threads were employed at the ends of each bar. So in total, this specific specimen employed 4 SMA bars, and there are at the two ends 2 fixed plates, and in the middle there is a moving plate which is attached to a piston, which actually takes the cyclic load in tension or compression. So at any point of time of the loading, whether the entire system is under tension or compression, the SMA bars will only take tension forces, so that they don't again buckle in compression. So we are just applying tension forces through the moving plate against the fixed plate. So the nuts here provide some locking mechanism which transfer the force in bearing against these plates into tensile forces into the SMA bars. So these figures just show a bit of details about the different components. As I mentioned, the SMA bars that are employed inside the system with the restraining nuts, the different plates, and again, as I said, this middle plate is the one that actually is moving under the test environment. So the figure here shows the test setup that was actually employed. So the universal testing machine was used to apply different types of loading, starting from quasi-static, simple quasi-static loading, tried different types of loadings and different rates, and then ended up with also applying some dynamic kind of loadings with again a strain and load effect. So in the following slide here we see the behavior of the system. So it was actually we were able to capture the numerical the behavior of the system in numerical environment using MATLAB, and then we are actually able to implement it in analysis and design software, as I will show. It's worth mentioning that, as you can see, the system could achieve almost perfect, very excellent self-centric behavior with good energy dissipation. So as I mentioned, although we could achieve it in a MATLAB code to achieve the experimental results, but for practice and engineers so that they can actually use such bracing system in design analysis softwares, we developed a analysis module and implemented it in S-frame software so that you can actually capture the behavior of the system using different parameters, including the initial stiffness, the superelastic stiffness, the different stress points. Also, this module actually includes the ability to capture the residual strains that may accumulate in the SMA, especially after repeated number of loads and repeated number of cycles. So little by little we can see that the SMA actually accumulating some residual strains. So this model can actually capture these values. So as I mentioned, the next step was is to conduct actually strain rate or different load rates into the system. So we started from the initial, which was 1 inch per minute, and then we went up all the way to 50 inches per minute. At each stage, we could always achieve self-centering behavior. The test was done on the very same specimen without maintenance, without doing anything. It is worth mentioning that with increasing the loading rate, the energy dissipation capacity was decreased, and that is most probably is actually attributed to the fact that SMA is a heat-sensitive material with higher rates. When you have higher temperatures, it reduces its ability to dissipate the energy and gets a little bit smaller hysteresis loops. So the next step was to actually conduct what is called the closed-loop dynamic testing technique. So in this proposed methodology, it starts actually with the fabrication and testing of the test specimen under quasi-static loads. And in most of the cases, as we know, this will be actually a reduced scale specimen. And then the next step involves the strain rate testing, again under quasi-static load, to characterize the numerical parameters that can be actually used after scaling up into the third step, which involves the numerical modeling and the implementation of this system in a 3D environment so that we can actually utilize it in a building. Now, after we have this building, we can subject it to different ground motions, different intensities, and then this is followed by the fifth step, which is acquiring the data that's obtained from different ground motions in terms of force and deformation. Now, the force deformation we have here is, as I mentioned, a full-scale response that's obtained from a full-scale building. Now, we can actually obtain the deformations of this hysteresis response with respect to time and scale it down, so we can actually input it again into the test specimen. Now, so here we are actually applying a dynamic kind of load, including the strain rate in each time step, and applying that to the test specimen again after scaling down the parameters. And then we will obtain the new kind of force deformation response, and then we scale it up and compare it to the original response that was obtained actually from the numerical model. Now, the steps from 3 to 9, all the way to 9, can be iterated more than once, so you can actually may not get a very good agreement between the numerical results and the experimental one, especially the one obtained from the dynamic testing, so that iterations can be done based on the initial stiffness, the energy dissipation, until a good agreement is achieved. And this is actually what is shown in the next slide. So in the very first trial, a sample of earthquake records were implemented, so we could not perfectly, to a great extent, actually achieve the experimental results. But after refinement of the model, as I said, after 2 or 3 iterations, we could at least achieve up to 10% difference in terms of energy dissipation and initial stiffness, a better agreement between the experimental and numerical results. And so this technique actually gives us a way to understand the dynamic response of the system in a way so that we, in cases we don't have a fully equipped lab with like shake table testing and all hybrid testing equipments as well. So in conclusion, as I showed, the piston-based self-centering bracing actually showed an excellent self-centering ability with minimized amount of residual deformation, which is a potential option for bracing systems in different buildings. The system again showed a stable behavior with different rates, with less energy dissipation, as I mentioned, with increasing the rate because of the inherent property of the SMA. And the new closed-loop dynamic testing technique actually proved to be reliable in predicting the dynamic behavior of the system. Now, I would like also to mention that the system is easily constructed and easily modified, so you can actually increase the number of SMA bars, the length of SMA bars to accommodate different forces or displacements that you are expecting that your structure will be subjected to. Before I end, I would like to acknowledge the support of different organizations, including NSERC, NRC Canada, S-Frame, and the University of British Columbia. Thank you again, everyone, and happy
Thank you, Anas. We have time for questions. Are there any questions for us? Yes?
Yes, thank you for your presentation. I have a question for the full scale of the self-centering system. If you need to compare between the cost, because you've spoken about the cost of the restrained buckling system. So if we need to compare, what do you expect about the cost of this system and the buckled one? And also about the simplicity of implementation of this one with the buckling restraint.
Thank you. That's very actually good question that we are actually trying to address now in the research. So constructability-wise, it is actually easier to build than VRB. VRB includes lots of complications to build, especially the debonding between the core and the mortar field around it. So that's one issue. The cost-wise, of course, SMA is still a quite expensive material. It's getting cheaper and cheaper every day, but still it's expensive, of course, compared to steel and concrete. But when we look at the bigger picture, including the resiliency and sustainability, like the life cycle cost of the building, And then, as I said, with all the damages that can actually accumulate with any other system like the VRVs or the conventional, and you look at the maintenance and repair cost, there is a huge potential that this system, even with the initial higher cost, it will be overall cheaper and more sustainable.
Yes?
A couple of questions that are perhaps related to each other. One is just on a material level, the SMAs, do they have a low cycle fatigue sort of issue the way that like, a BRB eventually, with enough cycles, will fracture because of low cycle fatigue in the core? Does anything like that ever happen with?
I myself didn't do low cycle fatigue with like huge number of cyclic loadings, but I've seen some research about that, and I believe it can take like thousands and thousands of cycles without fracture, but you will start seeing some accumulation of the residual stresses.
So the other piece then that's related to that in my mind is you talked about those residual deformations that you get. And from what I've seen, it seems the first cycles are where you get most of those residuals in the SMA, and then it kind of stabilizes, and you can even see that in your results. Would it make any sense with these braces to just run it through a few cycles before you implement it, so that you don't have to worry about the residuals?
Yes, of course. So that's one benefit actually. So you don't. The specimen itself, you can, which is actually this specimen as well. It's been tested and tested again and again. The same specimen. Now another source of the residual that deformations that you observe also in this system specifically, that it may generate some kind of gap, so that this locking mechanism. In this case, it was just manually tightened without any mechanical wrench or anything. So maybe after like a major event, some maintenance may be required to tighten the mechanism so that there is no slippage at all in the system. Yes?
Yes?
Since SMA is not as steep as the steel, did it, like in the seismic analysis you conducted, did it affect the total displacement of your building?
Yes, actually, in fact, it is, as you said, less stiff material, so it has more kind of ductility. It provides more ductility, so that the overall behavior of the building was actually obtaining more inter-story drift ratios, but it was still in the different guidelines limits. So, and the other thing that I mentioned, that actually you can easily modify the model, and you can increase the stiffness of the system itself, or you can just increase the number of bracings in the building to increase its overall stiffness.
About the machining the SMA, did you use a special machining or like bead to?
Yeah, actually it was a bit of challenge to machine them down, and now with our next phase we are trying to get them machined ready from the fabricator, because as I said, it's sensitive, heat sensitive material, so you don't want to apply too much heat while machining. So we like through some outsourcing some machinists, we could machine it with like normal stainless steel milling machine, and with applied coolant and oil, so that it was a slow process. It took lots of time, but eventually we could achieve what we wanted.
So since SMA has a low stiffness as compared to regular steel, do you see that it might be subjected to buckling under, if it's under severe earthquake loading, the SMA rod that you're using inside your piston-based system?
Well, not in this case, because it will not whatsoever have any buckling force, not even 1 kilonewton, because the system is built in a way, in compression, the bars are released, so they don't experience anything. They just take tension.
Okay. I have a question for you. What was the temperature rise in some of the dynamic cyclic loads that you were?
Yeah.
Because you mentioned that, but no numbers in terms.
Yeah,
of...
I didn't actually measure the temperature.
Oh, you didn't?
So yeah, but
Can
I mean,
you touch it, or it was too hot?
it was a bit hot. Yeah. So we didn't actually measure it. I mean, after we looked into the results and looked into the literature, and saw that actually the temperature affects that, but we don't actually measure it.
And the last question is, what are they at now in terms of the largest bars that they can build with constant properties through the thickness?
We have contacted several suppliers, and they all said they can provide up to 32 mm diameter. So yeah.
Okay, thank you very much.
Thank you.